Hi everybody, welcome back to Dave's Math channel. This is a video on another one of my daily math problems that I post on a regular basis on the Facebook group Classical Mathematics. And in this particular problem, I'm asking for integers up to 1 million, positive integers up to 1 million that are palindromes in both binary and decimal. And the solutions are on the slide, but I'll get into that. Anyway, just to be specific about this, here's a specific problem statement. I think I already said it. Find all positive integers up to 1 million that are palindromes in both binary and decimal. In case you guys don't know what a palindrome is, it's a number that looks the same when you reverse its digits. And, it has to be, the binary digits has to be palindrome as well as decimal. And that's a pretty big restriction, it turns out. As a matter of fact, I think there's pretty good heuristic arguments you can give that should be only a finite total number of solutions. You don't even need an upper bound, but I mean computationally you do, because you could be computing till the cows come home, or if you make your upper limit too big. That's why I picked an upper limit of 1 million. And, this is a problem. I don't know any better way to solve this problem than to use brute force. I mean, if it was just a palindrome in one base, that's easy. I mean, you just care about the last half of the digits in whatever base you're working in. And then the first half has to be the mirror image of that. So it's pretty easy to get palindromes in any fixed base, but to get them simultaneously in two bases, I don't know any better way than to do a brute force search, which is what I do here. So I first define some code. I mean, luckily in Mathematica, there's already a built-in function called palindrome Q that will test whether a given decimal number is a palindrome or a string of I guess it could be just an arbitrary set of objects, usually numbers, but it'll test whether that object is reversible, whether it's the same when you reverse all the characters. So we use both of those built-in mathematical functions. I first have this function I'm calling base B palindrome Q. And Q is usually a letter you use to indicate a Boolean function, a function whose value is either true or false. It's just a convention that's used in Mathematica. So what base B palindrome Q is, first I give the number that I want to see if it's a palindrome, and then I give the base B. So B has to be a positive integer, at least 2, and N has to be also a positive integer. And now all this function does is it first breaks up N into its base B digits. So, it just turns that into a list of digits, and then it tests whether that list is palindromic or not. So that's all this first function does, pretty straightforward. And then to test whether a number is a palindrome in both binary and decimal, you just have to test that it's a base 2 palindrome and a base 10 palindrome. Well, base 10 palindrome is given for free. That's just palindrome Q. And then that's the last part of this. This is a conjunction of two things. And the first part, we're just testing whether it's a base 2 palindrome. If it's base B palindrome Q N, 2, that just tests whether it's a binary palindrome. So this function will test whether the numbers we're given have the properties we want. And now all we have to do is go through a loop. So I have this function called binary and decimal palindromes, and then I have an upper limit, which I'm calling n max. I'm going to set that to 1 million. But all this function is doing is looping over n, going from 1 to n max, and testing whether all of those integers n are each of those is a binary and decimal palindrome. If it is, it adds it to this list. And it also has the base 2 representation as well as the base 10 representation. So the way you get the base 2 representation, you just use the function from digits, integer digits, n comma 2. Integer digits, n comma 2 are just the bits, the binary digits of n in order. And then if you put the function from digits, it makes it looks like a binary number, no list, just a number. So anyway, that's how this code works. And here's the result of running it. And it's pretty fast. I mean, even though it's just a brute force search, I probably could have made this a lot more efficient by just testing the last half of the decimal digits. I don't have to loop over every number in. That's what I'm doing, I'm looping over every number from 1 to a million. That's kind of a waste. I probably could have only looked at, the last three digits, or maybe in the case of a million. We don't care about a million because we know it's not a palindrome. But otherwise, we could just look at the last half of the digits, make a base 10 palindrome out of it. I didn't do it that way. That would have been more efficient because then you can just test whether each of those numbers is also a binary palindrome. But I did it the hard way. It only took about 2.5 seconds. And here's the result. And I think you can see that the numbers on the left, the binary representations, are all palindromes. They all look the same if you reverse them. And also the decimal representations are all palindromes. Kind of neat. And there's a total of 19 solutions. And one thing, one of my friends on the classical mathematics site, I forget his name. He asked me an interesting question. He asked me to come up with a asymptotic lower and upper bounds on the total number of solutions to this problem. Forget about an upper limit. And I actually did that. I did that. I'm not going to put this in this video because the analysis is a little bit complicated. But if you make a kind of a reasonable assumption, I think, and that one thing you have to notice is that all these numbers are odd. I think it's pretty to see that every binary palindrome has to be odd because it has to end in 1. I mean, it begins in 1. Every binary number begins in 1, so that means if it's a palindrome, it also has to end in 1. If it ends in 1, that means it's odd. So, and I think you can tell if you look at the numbers on the right, the decimal representations are all odd. So they have to be odd. They can't be even. But among odd, here's the assumption I made when I was doing the asymptotics. I assumed that for a given odd, any given positive odd integer, the probability that it's a binary palindrome and the probability that's a decimal palindrome are independent. And it turns out that in any base, this isn't too hard to prove. In any base, the number of palindromes up to some big limit, capital N, is approximately square root of capital N. But it's square root of capital N with a constant in front. And that constant I calculate the bounds, the lower and upper bounds on the constant, which depend on the base. But if you use those lower and upper limits, and then you multiply those probabilities together for binary and decimal, you get a fixed number that's between. It turns out that it should be between 18 and 32, according to my heuristics. We know it's bigger than 18 because here's 19 solutions. So my guess is there's probably at most 32 numbers, without any upper bound. They're simultaneously binary and decimal palindromes. I could be wrong about that. Maybe my assumption that the probabilities are independent is wrong. I don't know if that's wrong or not. But anyway, I just thought I'd mention that. Anyway, that concludes my video for today on binary and decimal palindromes. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you guys next time. Bye.